We talk about the weather all the time, but have you ever stopped to think about the weather on the sun? It turns out our star has these enormous hidden currents that shape literally everything from sunspots to the solar storms that can affect us right here on Earth. For decades, scientists were totally stumped about what was driving them. So how on earth did a 120-year-old Arctic expedition hold the key to cracking the sun's code? Well, let's dive in. So here's the mystery we need to solve. Deep inside the sun, there's this vast ocean of super hot plasma, and it's flowing in a massive planet-sized conveyor belt. We can see it moving from the sun's equator toward the poles on the surface, but then it has to return, somehow, deep in the interior. The big question has always been, what's the engine? What's powering this colossal system? Okay, first up, let's get a handle on the sun's hidden ocean, because this really is a star-sized puzzle. And as you're about to see, it has some very real Earth-sized consequences for all of us. Right, so by studying sunquakes, a field called helioseismology, we can actually see what's happening inside the star. And what we see is this steady flow of plasma on the surface moving toward the poles. But, basic physics tells us that stuff can't just pile up and disappear. What goes poleward must return. It has to dive deep and complete the circuit back to the equator. And for decades, that deep return flow was a complete and total mystery. And you might be asking, why do we care so much? Well, this whole conveyor belt system is basically the master clock of the sun. It's what drives the famous 11-year solar cycle. It dictates where and when sunspots pop up, and that, in turn, creates the space weather that can mess with our GPS satellites and even knock out power grids. The crazy thing is, for years, our best computer models just couldn't explain it. They couldn't make it work. It was so frustrating it even got its own nickname, the convective conundrum. So our best solar physicists are stumped. The most powerful models are failing. Where does the breakthrough finally come from? You are not going to believe this. It came from a 120-year-old observation about how ice drifts around in the Arctic Ocean. Seriously. Okay, picture this. It's the 1890s. An explorer named Fridtjof Nansen is on his ship, trapped in the Arctic ice for months, and he notices something really weird. The ice isn't drifting in the same direction the wind is blowing. Nope, it's always veering off to the right. He had a hunch it had something to do with the Earth's rotation, and later he challenged a young physicist, Vagn Walfrid Ekman, to prove it. And Ekman's solution became a cornerstone of modern oceanography. And the secret ingredient here is something called the Coriolis force. Now, it's not a real force like gravity that you can feel. It's more of a phantom force, an effect that only shows up because we're living on a giant spinning ball. In the northern hemisphere, it makes anything that moves, wind, water, even an airplane, get pushed slightly to the right of its intended path. So here's the elegant part, the beautiful balance that Ekman figured out. The wind blows across the ocean, right? That's a friction force. It starts to push the water. But as soon as the water moves, the Coriolis force kicks in and pushes it to the right. These two forces fight it out until they reach a perfect balance, an equilibrium. And the result? The water, on average, ends up flowing at a perfect 90-degree angle to the right of the wind that started it all. This whole thing is called Ekman transport. And this just perfectly captures the mind-bending leap in thinking that solved the solar puzzle. The researchers who cracked this actually wrote this in their paper, expressing their own sense of awe, that a theory born from just watching icebergs float around could possibly explain what's happening inside a star. It's incredible. But you can't just take a theory designed for a relatively shallow, flat ocean and slap it onto a giant sphere of burning plasma. That's not going to work. The old theory needed a major upgrade. And this is where things get really clever. The classic Ekman theory basically assumes the world is flat and only thinks about side-to-side horizontal motion. What these researchers did was create a generalized Ekman theory. This new version works in full 3D on a sphere, and this is the most important part, it doesn't just predict horizontal flow. It also predicts a radial flow, an up and down flow, and that little detail turned out to be everything. All right, so now we've got this powerful new theory in our hands. It's time for the moment of truth. Does it actually line up with what we see on the real sun? To even apply the theory, they first needed to find the sun's version of wind blowing on water. They needed to measure the friction, and they did this with a truly brilliant move. First, they built a computer model of a perfect sun, one with zero friction, and calculated how it should be rotating. Then they compared that ideal, perfect model to the messy, real-world data of how the sun actually rotates. And here it is, the big aha moment. The difference, that gap, between the perfect world of the model and the real world we observe, that wasn't an error. That was the signal. It was pure, unadulterated friction.
It was the signature of all the churning and dragging forces inside the star. They had found their wind.
So the whole process was just beautiful. First, they took the real-world measurements of the sun's spin. Then they calculated all those tiny deviations from the perfect model, those little speed-ups and slowdowns caused by friction. After that, they just plugged that friction data right into their new generalized Ekman theory. And the theory acted like a decoder ring. It took the friction in and spat out a complete map of the sun's entire hidden conveyor belt.
And the result? It was absolutely spectacular. The map of plasma flow that the theory predicted was a stunningly perfect match for the actual observations we have of that great solar conveyor belt. Just like that, the convective conundrum was solved. The driver wasn't some crazy exotic force. It was just a simple balance between friction and the Coriolis effect, the same thing Nansen saw in the Arctic ice a century ago. The code was cracked.
Now, this discovery is so much bigger than just solving one long-standing puzzle. It really gives us a whole new, unified way of looking at the sun, of seeing it as one deeply interconnected system.
What this new theory does, essentially, is build a bridge. It connects the physics happening right at the sun's surface with the dynamics happening way, way down deep inside. You see, the solar wind is constantly dragging on the surface, creating a bit of friction. And this theory shows exactly how that tiny surface drag gets communicated all the way down, influencing the flow right at the edge of the sun's core, in a region they call the tachocline.
And if you need more proof, check this out. The researchers found what they call a trifecta of torque. Now, torque is just a fancy word for a braking or twisting force, and they calculated this force in 3 completely separate ways. First, how much torque is needed to create the flow we actually see. Second, how much torque does their new friction model predict? And third, how much torque does our existing theory of the solar wind predict? And all 3, totally independent methods, gave the exact same answer. That's when you know you've really nailed it.
And as if that weren't enough, the theory even solved another mystery as a bonus. For years, we've known that the tachocline, that boundary layer just above the core, isn't a perfect sphere. It's kind of squashed. Well, it turns out those up and down flows predicted by the generalized Ekman theory provide the perfect physical reason for why that boundary is shaped exactly the way it is.
So, there you have it. From a simple observation about drifting Arctic ice to a grand unifying theory of solar weather. It's just an amazing reminder that sometimes the biggest cosmic mysteries are governed by the same elegant, simple principles we see at play right here on Earth. And it leaves you wondering, what other secrets buried deep inside other stars are just waiting to be unlocked by the simple, fundamental physics of friction?